It is my pleasure to welcome all of you. Our guest today is Professor Dominique Lambert. He is a professor at the university, which is called Faculté Universitaire Notre-Dame de la Paix à Namur in Belgium. And as you can see, he is a member of the Académie Royale de Belgique, class des sciences. And his interests are very broad. It's very difficult to find a field connected somehow with philosophy and science in which Dominique would not be an expert. Usually we are considering the question of unreasonable effectiveness of mathematics in physical sciences, the famous formulation of Wiener, but Dominique expands that, extends, and asks today, is there any unreasonable effectiveness of mathematics in biology? Dominique has done also some work in mathematical biology, together with the University of Geneva, as far as I know. And I think it would be interesting for us to listen to what he has to tell us.
Thank you very much, Michael, for such kind invitation. And I want to speak today about this problem. And in fact, I will follow these tracks. If you are completely lost in my slides, then you can here find the main stream of my thought and of my talk. And I want first of all to address the question of effectiveness of mathematics in natural sciences. But you know probably, and Michael said that to you, that in fact, indeed, this term unreasonable effectiveness was used by Wigner in a paper in 1960, where he said, well, there is an unreasonable effectiveness of mathematics, in fact, in physics, but unfortunately, he said at the end of the paper, it is a wonderful gift. In fact, there is no explanation to this. It is marvelous, wonderful, but in fact, he did not produce any explanation of this fact. We know that effectively there is some miraculous or unreasonable effectiveness of mathematics in physics, but we can now and today address the question to know if there is such unreasonable effectiveness of mathematics in biology and, for example, in molecular biology. And I want to show you, first of all, that there is maybe not a complete, but there is some unreasonable effectiveness in some field of biology. Maybe not in whole field of biology, but in some field of biology there is indeed an unreasonable effectiveness. But first of all, we have to ask the question, what does it mean, effectiveness in mathematics, in biology, or also in human science, if you want to address this question in these fields too. In fact, I have here some quotation of Evelyn Fox-Keller, an important philosopher of biology, who said, physicists come from a tradition of looking for all-encompassing laws, but is it the best approach to use when probing complex biological systems? And in fact, in his book and papers, she tries to refute the idea that in fact there is some analog effectiveness of mathematics in biology. Biology would be a very special field, and this unreasonable effectiveness of mathematics would be not present, in fact, in biology. I want to address some critiques to such a quotation, such a position, and in fact, I want to quote also this quotation of Manfred Eigen. And Manfred Eigen said, well, there is a problem with biology, because biology is evolution and evolution is history, and maybe we are not in the position to reconstruct all the history of life, all these details, contingent detail. But his position is to say, well, maybe studying the traces of biological history, maybe this will provide enough clues to allow one day the construction of those equations for the unknowns in biology. Then you have two positions. One position of Fox-Keller saying, well, no, there is a deep difference between physics and biology. It's impossible to have an unreasonable of mathematics in biology, because general theories are not working there. And there is here some other position saying, well, maybe one day we will get the general laws, and we will describe the mathematical law of life. And Manfred Eigen has developed, as you know, a kind of dynamical system in order to model evolution called hypercycle. Then we have two positions, and I want to go. My position is, in fact, in between. But first of all, I want to address the question of effectiveness of mathematics. What does it mean? What does it mean? In fact, mathematics is very effective and successful in natural sciences, or even in some field of human sciences, when mathematics provide a description. But to describe is not to explain. Then, in fact, you can give a marvelous description without explaining anything. Okay? You can give statistical description, but in some situation you are not able to produce any general principle to explain. Mathematics can be very successful when they describe some organism, some complex system, but there is some limit. In fact, mathematics are successful not only when they are describing situation, but when this mathematical theory lead to empirical prediction. When the model describe and predict, then you are in fact you are wanting to say, well, mathematics are very efficient, mathematics are wonderful in this field. But you can produce some nice description, and you can predict without a true model. You can, for example, the epicycle of the Greek is a nice example, but there are many examples where a mathematical theory gives very good prediction without giving the right explanation and without being true. Then it is not sufficient. In order to be effective, mathematics have to describe, to give adequate empirical prediction, but they have to produce an explanation from some clear and meaningful principle. In fact, this is not, 1 and 2 are not sufficient. In fact, the deep effective mathematics in science produce some kind of explanation. For example, in physics, you can describe fundamental interaction using, for example, some symmetries, some gauge symmetries. And this is a description, but this is only a description. So it is not only a description. Because in fact, if you describe forces interaction by symmetries, in fact, you explain the origin of the interaction. In fact, you reduce the existence of force and interaction to some deep principle and deep property of the space on which you are working. Then force is an interaction would be a consequence of some deep property of the space. In fact, you have effectively a description, but this description gives you an explanation if you want. Of course, you have to explain why these symmetries are present, but this is one step towards an explanation. Then, in order to be successful, effective, mathematics have to give a description, lead to prediction, but they have also to give an explanation based on some general principle, shedding some light on the phenomenon. But it is maybe not sufficient. In general, unreasonable effectiveness of mathematics in science means also the generativity of the formalism. It means that if you have some good mathematical formalism, this formalism enable us to suggest new ideas, new theory, generate new protocols, and so on. And in fact, all these features define what I can call the effectiveness of mathematics. If you have all these characteristics, then we can begin to speak about a kind of unreasonable effectiveness of mathematics in the field. But why? Why? Because in fact this is nearly equivalent to say that we are able to reach an element of reality. All these in fact correspond to the possibility to grasp some element of reality. But what does it mean, an element of reality for a physicist? An element of reality is minimally characterized by at least three properties. First property, if you have an element of reality, you have necessarily some unity and some coherence. If you have, you say, well, this is an element of reality. This is why you have some kind of unity. This table and this computer do not form an element, directly one element of reality, because there is no coherence between the computer and the table. In fact, what characterizes minimally an element of reality is, first of all, a kind of unity and coherence. Okay? But this is easily described by what mathematicians are calling structure. This, in fact, is metaphysically the problem of form, if you want, the form, the formal cause, if you want. And in fact, it corresponds in mathematics some kind of this coherence is described by structure. It means a set with some kind of relation or operation which build a coherence on a set, on a collection of things. But an element of reality, in fact, these are minimal criteria to see or to recognize an element of reality. If you have not this, you have not an element of reality. But you have not an element of reality if you have not minimal subsistence, some minimal existence, if you want. If, for example, I'm looking to this computer, and every second the computer becomes an animal or a car or a building, I will say no, it is not a real element of reality. It's maybe an illusion, maybe something else, but not a real element of reality. Element of reality asks for some continuity existence. And in fact, at the level of mathematics, this means that element of reality is described by some invariance. If you have no invariance, not at all some set of invariant, you cannot find an element of reality. Element of reality presupposes some kind of invariance. Okay, but an element of reality, in order to get an element of reality, you need also capacity of interactions. If there is some reality, the physicist will say, well, we can interact with. If you say, well, I believe in the existence of quarks, why physicists believe so hardly in the existence of quarks? Because you can make some interaction in the LHC at the CERN, and you can interact with, in some situation, with quarks. Then this is, if you want, necessary but not sufficient, but necessary condition to recognize some element of reality in science. Okay, minimal condition to face an element of reality. But it happens that these minimal conditions, epistemological condition, corresponds adequately to some kind of property of mathematical theories. For example, unity and covariance are described by structure, but continuity existence, okay, is easily described by invariance. And in fact, you know that in mathematics, invariants are very, very important. When we have a theory in mathematics, immediately we are finding transformation which exhibit some invariance. And for example, topological invariance, algebraical invariance, and so on. And interactivity is described easily by dynamical systems, evolution equation, and so on. Something which describes the possibility to evolve and to interact. Okay. In fact, this is to clarify. I'm not saying here that this is an absolute definition of unreasonable effectiveness. I propose to you minimal criteria saying, well, we can speak about an effectiveness or unreasonable effectiveness of mathematics when we have these four features, and in fact, this feature, in fact, corresponds to the possibility to grasp an element of reality, but an element of reality can be described by this, and this can be formalized in mathematics by this kind of object. Then we can say the following. We can speak about an unreasonable effectiveness of mathematics in biology, if you want, if, for example, you can identify some structure, some mathematical structure, and maybe some invariant which can characterize an organism, a subsystems of complex biological systems, and so on. If you can, it means that if you cannot extract or find some invariant, or if you are not able to extract some structure, some set with relation mathematically described, then you cannot in fact face the unreasonable effectiveness. I want to say immediately a very concrete example. I can address this question for human sciences if you want. For example, economy, or more precisely to finance. Okay? In fact, is there some nice, wonderful, effective description of financial evolution of an option, for example? And you know that in fact there are some description using Brownian motion and so on. But you know that the last crash is also due to the fact that mathematicians, financial engineers, were using some kind of standard Brownian motion to modelize the oscillation of if you want the value of an option in order to compute the risks. And in fact they use only Brownian motion, but in fact you can have large oscillation, and in fact the computer are only using this kind of motion, and they, for example, they don't use some stochastic process describing large oscillation, the Levy process, and they are not able to foresee the crash. And this is mainly due to that the financial and economical movement are not submitted to some real strong invariant. You have many fluctuation which are due to in fact maybe an irrational action of some human being, and at each moment you can have fluctuation, perturbation and so on, and the general description of finance is not so easy to describe by mathematics due to the fact that it is nearly impossible to grasp a set of complete invariant of the behavior, because in fact there are many contingent parameters destructing the invariance. The question here is, in biology, can we extract some general structure, some invariant describing, for example, cells, organisms, ecosystems, and so on? If yes, then maybe we will find some wonderful, efficient, effective mathematics in biology. Okay, I want at this step of my talk quoting this quotation of Robert Bob May, Use and Abuses of Mathematics in Biology, published in Science. And he said this: in the physical sciences, mathematical theory and experimental investigation have always marched together. Mathematics has been less intrusive in the life sciences, and the point is, possibly because they have been until recently descriptive, statistics mainly, descriptive, lacking the invariance principle and the fundamental natural constants of physics. In fact, in physics, what is characteristic is you have general laws, invariant or covariant under general transformation, and these transformations are connected with invariance. And in fact, the fact that you can grasp some invariant means that you can do some repeatable experiments and so on. And in fact, Bob May, an ecologist, say, well, maybe in biology, as in economy, finance, psychology, sociology, and so on, maybe it is not possible to grasp some invariant, because the field is not submitted to a kind of general invariance. The characteristic of the field, of this field, could be the fluctuation, the chaotic behavior, and so on. Okay? Well, I want to address this question. Is it possible to find mathematical tool related to structure, coherence, invariant, subsistence, continuity existence, dynamic systems, interactions and so on, which are connected to every empirical data coming from real biological system. Okay? Is it possible to find such a mathematical tools? This is the first question. If yes, then we can say, well, there is a wonderful and unreasonable, maybe, effectiveness of mathematics in biology. Second question, are the tools identical to those used by physics? Because you can say, well, it is true, there is unreasonable effectiveness of mathematics in biology, but the tools and the theories and the concepts are very different. In fact, this position was the position of Niels Bohr. Niels Bohr believes that, in fact, biology is submitted or described by another kind of quotation mark in physics or mathematics. Are the tools identical or not to those used in physics? Third question, or are some of them completely very of new nature, and what are these new concepts which are used, which are necessary to describe biology? Is it necessary to coin very new mathematical tools to describe biological system? Is biology simply a physics of complex system with some special contingent initial and historical condition? This is also a question. And are there mathematical law of biology as such? If biology is like physics, we can address the question to know, are there some general mathematical laws describing organism, for example? And this was an idea of Volterra. You know that Volterra, the Italian mathematician specialist in integral equations and so on, Volterra of the famous Volterra-Lotka in ecology, model in ecology, Volterra has written a beautiful paper in which he tried to describe the behavior of ecological system using one variational principle, like in physics. In physics you use the principle of least action, and then Volterra wanted to find a kind of principle of least action in biology. Of course, he realized that it does not work, and maybe we will come back to this question in certain time. Okay. In order to answer the question, the first question, is it possible to find nice mathematics describing biological system? Well, let us explore the biological universe and the history of biology to know if there are some beautiful mathematical description of biology. And you know that this is a nice example at the beginning of the 20th century. Darcy Thompson, who was a zoologist, a Scottish zoologist, but he was also an Aristotelian philosopher, and in fact he completely did not appreciate Darwin theory, but his ideas in this beautiful book on growth and form was to try to explain all the biological forms in term of simple mathematical concept. And the idea is, in fact, every biological form corresponds to a mathematical form and maybe to a physical system described by this mathematical form. And I don't know if you have ever read this book. It is a marvelous book, and this book was in fact influenced by Goethe. And this book was influenced by Goethe philosophy, but in fact afterwards this book influenced Waddington and also René Thom, the mathematician who worked on singularities, catastrophe theory and so on, bifurcation. And also this book was very influential for Alan Turing. I will come back to this. And you see, the idea of Thomson is to say, well, you have some kind of variety of forms, okay, and all these forms in zoology, for example, can be obtained by some transformation of one archetype. And you see, this is a reminiscence of Goethe. Because you remember the Urpflanze, for example, the Urtier in the philosophy of Goethe. Goethe imagined that you have a kind of archetype. Goethe is not an evolutionist, but he said, well, we have an archetype, and whole types of animal and plants and so on can be connected to one archetype. For example, all plants have one stalk, leaves, and so on. You know, the tree, all the trees are nearly the same topologically, if you want. And this influenced Darcy Thomson. I said, well, in order to get in a class of animals or in a class of plants, in order to produce, to explain all the forms, you have to transform some grid inside which the archetypic form is placed. And this kind of transformation is in fact conformal transformation. Conformal transformation is transformation which combines dilation and contraction, which preserve angles but not length. Okay? And for example, here you have in Darcy Thomson book some example with fishes. You take this fish and then you produce this one by an inclination, this type of coordinate transformation, and you try to reproduce all the forms in the sphere, in the biosphere. But you know, here, this is a nice description. And you can prove effectively that Darcy Thomson was a very concrete zoologist. He has in his room a complete collection of animals that you can find in the sea near Scotland and so on, along Scotland. And in fact, Darcy Thomson checked. He has theoretical model, and then he check in his collection if it is true or not. This is a description, but of course at this time it was not an explanation. But you can describe, yes, and you produce the true forms, but it is not an explanation. But now in fact, this model can be connected to some real biology, and in fact this transformation of dilation and contraction can be connected with the action of networks of architect genes like the OX genes and so on. In fact, these master genes are responsible for the spatial and temporal map of the organism, and you can prove that if you do some mutation of this master gene, you can in fact modify the map, the forms of the animals. And in fact this description was not an explanation, but it is interesting that it is not an explanation at this time, because at this time it was impossible to connect mathematical invariant with some concrete biological reality. And this is very important, because you can construct many theories in order to reproduce biological system, but this theory has to be connected to some parameter, to some concrete reality handled by biologists. If not, this is not a real explanation. This is only a description. And this book on growth and form influenced very, very much Alan Turing. And Alan Turing saw in Darcy Thompson's book this picture. And the problem of Darcy Thompson was to explain why are there two kinds of lines, of such lines on the zebra. In fact, we know that there are two types of organization of lines, black and white, two types. And why two types of zebra, if you want? Why not 4? Why not 6? Why two types? And Turing in his project, you know that Turing wanted to make an artificial man. This was in fact the aim of Turing before the Second World War, and it explained why he has developed the computer theory, because he wants to in fact to build an artificial man, and then he has to conceive an artificial brain and an artificial body, and unified both. And in fact, his work here is connected with the construction of an artificial body. How is it possible to construct an artificial organism and explain the several forms, the different forms of an organism? And he developed what we call now the Turing model. Doesn't matter the detail, but I want to illustrate what Turing was doing. The Turing model is simply that. You want, for example, to explain the forms on a butterfly. Okay, you have seen that many butterflies have some nice spots and so on, and you want to explain why there are some spots. And to classify all the form, exhaustive classification of all the forms on the wings of a butterfly. And Turing gave the explanation. And in fact, the explanation is the following. Let us just imagine that in place of the spot, I am here. Yes, I imagine some guys setting fire here. Here, some guys are setting fire, and fire is diffusing. Okay, I set fire here, is burning here, and the fire is diffusing. Okay, in a forest, for example, and this in fact activate the firemen, and the firemen are coming, and they are destroying the fire, and the fire is limited there. But in fact, the firemen are also diffusing on the field, and maybe some sparks is going there, and the fire is burning here, and these activate firemen, and firemen are coming, trying to extinguish the fire, and so on. And you see that if you have diffusion of fire, can diffuse in the forest, and diffusion of the firemen, then you can get some structure like spot. And this is described mathematically by this. This is the fire. This is the simple model of Turing. The fire activates the coming of the firemen. Okay, there is a positive interaction. When the fire is started, the fireman is coming, and when the fireman is coming, well, the fire tends to disappear. This is a negative interaction. And in fact, you see, fire activates the coming of the fireman, and the fireman inhibits the development of the fire. Okay? and maybe the fire is activate itself, okay, and we have diffusion. And in fact, Turing realizes that if we are playing with diffusion constant, if you are playing on the speed of diffusion of the fire, on the speed of the fireman, if you play with such constant, you can reproduce a great diversity of forms. And for example, he used what the mathematicians are calling now reaction-diffusion equation. He realized that if we solve this equation describing this little system, if we solve the equation on several animals, okay, because it's different to solve an equation with this border than to solve this equation on this type of forms, okay? The border are very important in the solution of partial differential equation. And Turing remarked that we can reproduce nearly all the forms on the pattern on the mammals, or classify all the forms of the butterfly using this description. And in fact, this is interesting because this is a description, okay, but at this time we have no real biological explanation. But we have extract some structure, okay, general structure, given by reaction diffusion system, and we have some characteristic invariants. Okay? Because if you change the topology of the animal, you change the form. And for example, if you have noticed, maybe, I like very much concrete biology, but you have, for example, remarked that if you have a cat, okay, if you have a cat, you have here the queue, on the queue of a cat, you have mainly some stripes. It is very rare to get spot on the queue of a cat. Why? In fact, this is a question of differential geometry. When you change the manifold, the properties of the manifold, this is a kind of cone, if you want, then you change the solution of these equations, and you can explain why you have such and such form on a butterfly, on a mammal, on the queue of a cat, and so on. Then it is very nice, and now we can have a complete classification of forms, not only on mammals, but for example here on snakes, and this is extracted from one of our preprint in collaboration of this laboratory of artificial and natural evolution in Geneva, Professor Milinkovic, and in fact we solve the equation and check the forms. Many persons in the world are doing this, but what we are doing was to solve and to check on some very concrete animal. This is an animal extracted from some real connection. And in fact, you can connect this model, this structure and invariant, to real biological system. In fact, in order to get a real explanation, all these invariant and structure had to be connected with some biological reality. And for example, the parameter in the Turing model can be connected with some genetic networks explaining the production of, if you want, the chemical product who are diffusing on the coat of the animal. And this produces a wonderful classification of the patterns on the animal. 40 years ago, biology, Monseigneur Lemaire said, well, I don't like nuclear physics, high energy physics, because there are too many particles which are not unify, it is like entomology. But now, if Monseigneur Lemaître would come here, he would say, well, entomology is nice because now entomology is unified, in fact. We have extracted some kind of general structure and general mechanism in order to think about the coherence of this part of biosphere. And this is one example. This is a crocodile we are studying in Geneva, and the problem is to explain why do you find this type of scales? Could you explain why such type of polygons appears on such type of animal? In fact, it is very dangerous to make such kind of mathematics and to check. Effectively, he is sleeping here, but in fact, it is possible to use a connection between genetics and, in fact, Evo-Devo theory, evolution and development theory in biology, and the theory of chaotic graphs in order to explain the form on the crocodile. I'm not entering in the detail, but I want to suggest that now we have some description of some forms, and we have reached such a position that we are able to describe by wonderful mathematical theory the generation of such form. What is this? Do you know what is this? Maybe biologists can recognize this. No? It is a mushroom. A mushroom. This is a mushroom. But you can see the marvelous organization, geometrical organization of this mushroom, which is growing, and we have here a polygonal system, and we can start from the hypothesis of Darcy Thompson, saying, well, this can be explained by geometry and topology of graph on a sphere, and it happens that we can connect this with real biological process, and we can extract some structure, some invariant, and connect them with real biological process. And I want to give you one example here. This is a very nice connection between a very, very important, very deep theorem in differential geometry and the classification of the tortoise. And this is a nice, very nice result found by Gábor Domonkos and Peter Várkonyi, Hungarian biologist, and they are discovered the following thing. In fact, you see here, this is a flat. This is a flat, nearly flat animal, the flat tortoise. And in fact, the problem is to explain the self-writing of tortoise. Okay, how is it possible to pass from this position, okay, with the shell on the floor, okay, to this position, normal position? Okay. In fact, in order to do this, this animal has to produce has to, in fact, to consume a great amount of energy, because it has to reach a potential barrier to fall, okay, in this valley. Okay, you have here a process which in fact involves some kind of physico-biological movement. But in fact, biologists knew that in fact there exists some class of tortoise which are very happy because a little movement is sufficient to produce this self-writing. Why? Because the shell of this Indian star tortoise, the shell is approaching a form which is known in differential geometry as, if you want, approaching the form called monostatic solid. And this monostatic solid was in fact found by the famous Russian geometer Arnold. And the problem is the following. You see, in dimension 2, you have here this system, and you have here a height weight, and this structure, okay, this game for children, is oscillating. Okay, and in fact there is one stable point, and the head of this guy is an unstable point. And there is one stable point and one unstable point. In 2 dimensions there exist some solids inhomogeneous, solid with one stable point and one unstable point. And the question addressed by Arnold was, and in 3 dimensions, does there exist some solids with only one stable point and only one unstable point? In fact, we can find many solids with 2 stable points and two unstable points and 2 stable points. Okay, let us imagine a rugby ball. There are many stable points and 2 unstable points. But does there exist a solid which only one stable point and one unstable point? And Arnold conjectured that yes, it is. And in fact, this solid is like this, and this is very interesting, because if you have only one stable point, okay, it's very easy to go towards this stable point. You have only one unstable point and one stable point, then in fact a little movement is sufficient to go to the unique stable point. And in fact this solid is nearly approximating some shells of tortoise, and maybe it was favored by evolution, because a very little movement is sufficient to explain why it is easy to do self-righting of the tortoise. And in fact, specialists of such animal have carefully studied, in fact, the forms of the shell, and we can prove that some tortoise has such a monostatic structure. But this is a very if you are interested, I can give you the reference, but it is very nice geometrical object. And all over the living world you have nice form. And now another example is the use of knot theory in order to understand some knotted configuration at the micro level. For example, you have in bacteria some kind of DNA which are knotted, which are in fact like some knots, and you have also knots here, but not real mathematical knots in zoology. And we know now that we can apply knot theory, which is a topological theory. We can apply such theory and the theory of braids and the knots of the tie, for example. This is a mathematical theory, and you can use this theory and the theory of ribbon in order to explain such configuration. You have such kind of configuration in the DNA, and in fact some properties of replication of DNA can be explained only by some topological property of knots. And this was also studied, in fact, by Darwin. But in order to explain some helicoidal forms in the plants. You know probably that Darwin was also a great botanist, and observed the spirals in the plants, and in order to explain all the spirals and how the plants are spiraling towards the left and towards the right, we can use now this knot theory. Then in fact, we can say all over the living world, and even at micro level, you can discover some regular structure, mathematical structure. And one additional example is here graph theory. You know that the genes are interacting as a network of interacting genes, and we can model here. This is a part of the genetic network of the ursine, and you can model this genetic network by the theory of graphs. And you can study carefully the property of these graphs. And for example, you recognize here a random graph, and here, for example, a scale-free graph. For example, if you discover this structure in biology, you can predict immediately that if you have some mutation which cut a link between two genes, it's not so important. Because if you cut a link in a random graph, then there is always another pathway to connect both nodes. But here, for example, if you have some hub, if you cut here, all the systems is broken and so on. And now we can use graph theory in order to describe genetic networks or proteome and so on, proteomic networks, and to predict the behavior of the system. And now it's very useful to study in biology such graphs and to predict the behavior of such system. And we can also put on this graph some dynamics, and we can study some energetic behavior of the system. I do not enter in this detail, but I want to show you here Waddington, and Waddington was also influenced by Darcy Thompson. And one reference in this field is the book of, for example, of Stuart Kaufman, who tried to describe some important feature of the networks using graph theory. But what I want to stress is all these descriptions are not at all real explanation in biology if all these descriptions are not connected to some real biological system. If this is only a description from outside, is not sufficient. All the mathematics who are in fact predictive now are not only wonderful, but are connected to some sub-biological system. And in fact, if you look this is another example which predicts the different forms of the cells. You can do this with differential geometry and optimization, and you can connect this description with real structure of, for example, of molecules, of the membranes, and so on. But in fact, what we realize that in fact all these descriptions are not sufficient to understand the organism, because we have to connect. An organism is a complex system at several scales, and in fact mathematics are not efficient if they remain only at one sub-level, because the essence of life is in fact a coupling of many levels. And the problem is, well, at one level you have wonderful mathematics. You can predict the form on the coat of mammals. You can find wonderful mathematical theory at micro level. You have marvelous predictive theory to predict the effect of the mutation on the network, genetic network described by a graph. But the problem is biological organism is not a reality at one level. In fact, what the essence of biological organism is a complex system with many interacting levels. And the question is there any mathematics to describe all these interacting networks? And in fact, now we know, if we study carefully mathematical theory in biology, that in fact we have no general structure to understand this coupling of all the scale. We need a kind of multiscale approach. In physics and chemistry there exist some multiscale approaches, but what are the characteristics of such multiscale complex theories? In fact, characteristic of such systems is, in fact, there exists some description of multiscale system, but the characteristic of such system is, in fact, that there not exist some unique fundamental laws. We are in a situation which is not completely the same as in physics. We need some kind of statistical description, multiscale description, and in complex systems the initial condition, the border condition, the fluctuation and the history of the system in fact are very important. And then we are in fact in a system, in a situation which is not comparable to the usual fundamental physical one. Why? Because in fact in complex system what is very important is coupling between the level, but also the fluctuation and the history of the system. And in fact what can differentiate biology from physics is the fact that not that in biology you have no structure, you have no invariant. No, you have structure, you have invariant, etc. But in fact, in physics, what is very important is general fundamental laws. Of course, initial conditions are very important, but what is central is first of all the fundamental laws and an equation. And then you put inside the initial condition and you solve the equation. But what is considered as fundamental is law and symmetries and so on. But in a complex system like in biology, you can describe this system as with statistical mechanics and so on. But what is important in biology is in fact initial conditions, history, and not at all fundamental laws. This is the opposite, if you want. In physics, law are very important, and in fact initial conditions are ingredient to solve the equation. But in fact in biology general laws are not so important. You have not a Dirac equation of the biology. Okay? But in fact what is very important is in fact the fluctuations, the history of the system, because you can have a general combinatorial theory saying, well, we can have such evolutionary tree, or no, this is one possibility, or no, this is not this is this, and so on. In fact, you can have a combinatorial theory showing you all the possibility, but in fact the real biology is, for example, this. But what does explain this? Why this tree and not this tree? In fact, the difference is due to fluctuation, to contingent situation. In fact, this is due to history. And in fundamental physics, the weight of history is less, because you can consider that fundamental laws are at the unhistorical, some kind of unhistorical status. But in biology, the description of the precise evolutionary tree is due to history. And in fact, the problem here is the following. In fact, we have here not a difference based on the unreasonable effectiveness of mathematics, but we have, and I propose you that for the debate, the difference is not the fact that here in physics mathematics are wonderful and here in biology mathematics are not wonderful. No, this is not the case. The difference is between the fact that in physics fundamental laws are very important, and the historical contingent things are not so important. But here in biology, laws are not so important, but the initial condition and the history of the system is very important. Question now, is there any evolution of science able to unify both? And in fact, to avoid the distinction between historical and unhistorical science and in fact this I come back to a famous quotation of Wigner. Wigner said that in physics you have the law and the initial condition, and in fact the problem is to know if the initial condition can be derived from fundamental laws, or if laws and initial condition are two ingredients which cannot be unified. If you cannot unify initial condition and fundamental laws, then you have a basis to understand the difference between biology and physics, if you want. Because in biology, the explanation of the precise evolutionary tree is due to some fluctuation initial condition, if you want. Of course, you can say that cosmological evolution is depending on initial condition too, but usually in physics, what is important is fundamental symmetry and laws. Okay? And what is important in biology is not for example, a biologist will explain why snakes have no legs, for example. In fact, snakes had legs. Okay? Yes, because snakes are derived from lizards and so on. They had legs. Why is there some process leading to the loss of the legs? Okay, but this is due whole contingent fluctuation, situation, environment, and so historical thing. There is no general theory explaining that from the Big Bang you can compute with one equation a solution showing you that now snakes have no legs. No, it's due to history. It is an historical science. And my question is, I don't know the solution, but is this difference fundamental? Maybe related to the difference between contingency and necessity. Is this fundamental or not? If it is not, then we can think about a general mathematical formalism explaining biology, okay, like physics. And if we have to respect this difference between contingency and formal necessity, then we have two kinds of formalism. And in fact, physics only cannot explain all biology. And maybe this problem is a central problem for the mathematization of human sciences. Because my opinion is morally that in fact we have to respect this kind of division. Because if not, then it would mean that human history would be a science, can be mathematized. And I cannot imagine that human history can be there is no logic of history. But you can say yes, we will show a logic of history. But this is the debate. My proposition is to propose that in fact even in physics there is a difference between fundamental laws, symmetries, and some ingredients which are initial condition and condition of frontier, border condition, and so on. And in fact, in biology, these conditions are very, very important, more important than law. Okay, I thank you for your patience.
Thank you very much. It was very interesting. And now. Questions, comments, contradictions, and
I welcome.
You're welcome. Yeah. So perhaps I will begin the discussion. I think that qualitatively, at least, there is a certain bridge between this part and this part. Mainly, if you look at the history of evolution of the biosphere, say. You can say that it is ruled by physical law. Mm-hmm. Physical law is the following: that biosphere or biological evolution is a dynamical system in a mathematical sense, of course, extremely complicated, dynamical, non-linear dynamical system, far from equilibrium and open. And of course, this is qualitative, but somehow in the background there is a physical law. And this explains why it's so difficult to mathematize it, because it is non-linear. Mm-hmm. Non-linear processes are always very difficult. Mm-hmm. And it is far from equilibrium and open. That is to say, it is open for fluctuations. Mm-hmm. And in all non-linear open systems, even in physics, external influence, perturbing influence, is extremely important, and also it contributes to formation of structures. Mm-hmm, mm-hmm. So, just for the sake of discussion, my thesis would be that it is only the difference in degree.
Yes, because here you have the both ingredients. Mm-hmm. Laws and initial conditions, but the important is stressed differently. Yeah. Because you can say, for example, engineers knows very well situation where history is very important. If the resistance of this building is modeled by some kind of historical procedure, then in fact in resistance of materials, in continuum mechanics, you use some historical process. But usually, in fundamental physics, it's difficult to introduce this historical and contingent thing. But maybe I see what you think about. Maybe the fundamental law can explain some kind of fluctuation, which are maybe not, which cannot be precise by experiment, but which are.
What is very important is natural selection. Mm-hmm. In the process of evolution. But natural selection, from a mathematical point of view, is interaction of a dynamical system with an open environment.
Yes.
So it is also a mathematical game.
Yes, but the problem is to know if there is some mathematization of the precise effect of the interaction.
Okay, I would invite you to contribute to that discussion.
I have a certain difficulty in relating these two schemes for the following reason. It's hard to imagine that you would kind of downplay the role of a law of science. If biology would be a science, let's say, without laws, what would that mean?
Yes.
That's kind of hard to imagine, because we can talk about different levels of, but you have, normally you would assume that in biology it's something like emergent structures, right? So at a certain level of complexity, you have new features which are not reducible to the features that are, emergence.
Yes.
And then, I mean, it can be true that you have to use different mathematics to, let's say, describe phenomena that are, visible at a level of complexity. So I do have a difficulty with downplaying the role of the law of science, because then what's left?
No, you're right. I have to precise my point of view. In fact, in biology, you have no fundamental global laws. You have, in fact, classes of universality, classes of laws, if you want. Because if you have some kind of a complex system, in fact, in complex systems, the renormalization philosophy.
Physicists will come and say that biology is reducible to physics.
No. In fact, what I can say that in biology, the point is, in biology, the system can be described as complex systems, and then you have some kind of renormalization philosophy, and in fact, with the renormalization group, what is important is not the theory, one particular theory, but universality classes of theory leading to some behavior, to some same behavior at one level, for example, at the macro level. And I cannot imagine that, in fact, biology is not guided by laws, but in order to describe biology, I think it is a dream to think about one fundamental laws. I think, as in the complex systems, we have to think about some universality classes of description leading to the same behavior at one level.
There could be one law, and you could never be able to formulate it, but there could be. I mean, why would you exclude one fundamental law?
Because
what's the reason for
just because it depends on this is very important. In physics, you have the same debate with the renormalization group philosophy. Either you think that there is a fundamental laws, and in fact renormalization is only a kind of procedure giving the result at each level, or you can say no, there is no fundamental laws which can be approached by human being, but there are some kind of approximating description which
fundamental philosophical assumption. I mean, that's as fundamental as it gets, I guess.
Yes, but I'm not sure that we can answer on the basis of science. We cannot answer what solution is. For me, for example, I can admit philosophically that in fact there is a kind of deep regularity, and then at the philosophical level, I could and I admit that there is some kind of regularity at work in biology, etc. But at the level of science, it's very difficult to answer the question: is there any fundamental laws, and then we can produce all the results, or there is no fundamental laws, and in fact there are only some universal classes of. Then you have completely right. In fact, if I remain on the scientific level, I cannot solve the problem, and if I solve the problem, I enter in philosophy.
The problem is, I cannot agree with this separation, very strict separation between biology and physics or chemistry, since also in physics and chemistry you've got a lot of systems where such emergent properties, behaviors can be found. And physicists have similar problems with describing it using mathematics right now. many physicists face the problem of trying to find the solution, perhaps other new mathematics to describe complex systems, measure properties between different levels. The same can be with biology. I mean, there's no difference, as Professor Keller said. It's just the matter of degree, nothing more. It's similar. I mean, you can have fundamental laws in biology. We don't know if there are not such laws. Right now, we don't know it, but you know, for me, biology is the state like physics was before Newton, and we have time. We try to apply mathematics to biology. It's still the beginning of the process.
Yes.
And we cannot say right now that there are not such laws, since we've got a lot of regularities. We've got a lot of, let's say, indications. We've got a lot of information which gives us some clues about similarities to some physical, or just like in natural science, some physics, such systems where we still have no good way to describe, to analyze, or even to explain some properties. This is very similar like in biology. So,
yes. But
I hope this will be the process which will lead us in the future to laws which will be very similar to the ones we have in physics right now. But we have to wait.
But yes, of course. But the aim of my talk is not to put a sharp division, because here you have the same thing, and my talk is.
You said that in biology, history is very important. In physics, material science also.
Yes.
Very important.
Yes, but it is a question. But I agree. No. But I agreed that in fact it is a question of degree. This is the same. But if you consider fundamental physics.
Yes. For interactions, for type of interactions.
Yes, and
in social physics,
I completely agree. In fact, this shows, and my talk shows that in fact the situation. In fact, my talk shows that in fact the best description now of physical system by mathematics is by the tools of complex systems. For example, biology is now the mathematical tools in order to understand mathematics now is multiscale approach used in chemistry, in engineering science, and in fact it is a kind of statistical mechanics. Then for me there is no a sharp distinction. But what I want to stress that in fact in the process of evolution of science, in physics, in fact, we have nearly nothing except in engineering science and in solid-state physics. In fact, we have nearly nothing emphasized the importance of historical things. And at the contrary, in biology too, I do not speak of evolution of the universe, but for example, if you describe something, the quarks, for example, fundamental interaction, in fact, does not. In order to describe quarks, you have not integral equation, in fact, summing on the history.
It's just fundamental physics. But when we talk about solid-state physics,
yes.
Next step about biology is very close to each other.
Yes, and in fact, the point here is to show that, in fact, the mathematics describing biology are not the mathematics describing fundamental physics, but the mathematics describing statistical, for example, statistical mechanics used in complex systems.
Fundamental physics also doesn't work in solid-state physics, let's say. So, normally we don't use solid-state physics, material science. We don't use fundamental physics. We don't talk about quarks.
No. Of course. This is why the interesting thing is the renormalization philosophy, and to know if this is a fundamental problem or only a problem of scales. But I agree completely. I don't want to split. No. Maybe I have.
I would like to turn your attention to the first part of your speech.
Yes. But I think no. Okay, fine.
Go ahead. We had a question: is mathematics so effective in biology? And we saw in the first part of the speech that in fact it is wonderfully effective. And we can see that mathematics begins to invade biology, which perhaps is the future of this science, which is rather unusual to expect something like that now.
Yes, yes. And I think that, for example, the first part of Malto is in fact dedicated to some local level, because you have.
So based on chemistry, let's say.
Yes, yes, yes.
That's why it's working very well.
Yes, yes, yes. It's true. It's true. And the second part was to say, well, we have to put all this level and
we have to fill the gap.
yes, yes.
What I would say was, we're actually missing a bit of the vertical mathematics, right? Because it doesn't. We don't know how to, we have a great difficulty in connecting the levels,
Yes,
right?
yes. This is in fact the aim now of the multiscale system. In fact, we have now, even in partial differential equation theory, we have techniques to couple some micro description to macro description, and you get something very interesting. New tools in order to realize what you are calling the vertical mathematics. And I think renormalization techniques is a vertical tool, because it connects all the scales. And maybe the distinction, I thank you very much for your remark, because in fact maybe we have to distinguish two types of mathematics. Maybe the horizontal one and the vertical one. The horizontal one, in fact, is a mathematics which is which describe one level.
It's working very well right now.
Yes.
Mathematics which can kind of different levels.
Yes, and for example, in multiscale approach, you connect, for example, in evolution of a galaxy, for example, you connect the chemistry of the elements, and with some high level dynamics, and you can connect it, and you use some techniques which in fact takes into account the interaction between the level. But it is true, maybe the distinction is to be made between the use of one level mathematics and the use of multi-level mathematics, maybe. And the second distinction is the problem of the reduction of initial condition to fundamental framework. But I don't know what are your feeling about this, because Wigner said it is impossible to reduce completely initial condition to fundamental laws. But Einstein thought the Überkausalität, in fact...
I think so far we have no, as far as I know, any possibility. We do not know any way to deduce initial conditions from general laws.
Yes, and
if you take the theory of differential equations, the initial conditions are always necessary in order to individualize a solution.
yes,
So it probably, it was a dream of Einstein indeed, because he was a holist. But well, in cosmology it's the same.
yes,
In cosmology, this problem is sometimes called the first cause problem. Whether the initial conditions, of course it is by analogy with theology, whether the initial conditions could be deduced from laws or must be imposed from outside
yes.
by the prime cause, for instance. So
Yes.
it is called sometimes prime cause
Yes.
problem in physics.
Yes, but but just imagine that we get the fundamental law of biology. Just imagine this problem remains. You have general law, but you need some initial condition or boundary conditions, and in fact
provided by cosmic environment.
Big Bang or anything like this.
With
Yes.
it's more difficult because there is no environment.
Yes, but let us try to explain the evolutionary tree, for example. You need...
Just like in dynamic systems, physical dynamic system, you have also beginning, initial conditions, initial point, starting point.
Yes.
It evolves, and you have
Yes, but
system.
but in complex system you have some chaotic situation.
Complex system is complex. I mean, that's all.
Yes, but there are some threshold where you have chaotic and unstable, far from the equilibrium state, and one single perturbation can...
Because you've got also a lot of physical system as disparate structures, which are
Yes.
far from the
Yes, in nonlinear thermodynamics you have this...
Yes.
Yes.
Similarities here. I mean, it's just
Yes.
difference between biology and physics. It's subtle. I mean, it's
No.
the difference.
I think the difference is maybe between vertical and horizontal mathematics and between laws and initial condition. Is it possible to throw away the initial condition or not?
I don't think so.
No, I don't think. I don't think so too. But the problem is evolution and in fact the feature of lives are determined.
Initial conditions.
Yes, but is this sufficient to determine the conditions at the Big Bang, or there is, in fact, if we start from a description, mathematical description of biology, even if we have such kind of general structure, the problem of the fluctuation and initial condition, what kind of initial condition are, maybe you can use a stochastic differential equation to manage fluctuation, but the problem is that evolutionary tree is depending on nearly one fluctuation at one moment. For example, the bifurcation which is leading to us.
It's exactly the same in physical system.
I think we should stop
Yes.
kind of discussion and leave it for later private discussion, because I don't think really you disagree.
Yes.
No. I think we agree, and thank you, because it precised my
You
my thought.
strongly agree. Okay. So perhaps there are some other short questions, because we must finish shortly, unfortunately. So thank you very much for extremely interesting question. Not question, but question as well. But your talk extremely interesting, and it's very provocative, and the problem itself is extremely important, and I think should be investigated both by philosophers, physicists, mathematicians, and biologists. So it is a sort of interdisciplinary project. Thank you very much.
Thank you.